All right, so we should have a recording going. All right, so plan for today, right, is we're going to spend some time working on the ADJ kind of module content. I'm hoping we can get through about 20 slides or so. This some good progress and put us in a good position for Thursday. So yeah, so in the past, right, basically we've been talking about a whole bunch of things, right? We started off talking about the different types of problems that are out there in the real world, right? We spent a pretty good amount of time on that, right? This idea of basically problems that are either open-ended or they're maybe ill-defined, right? So we spent some time on that, right? That was last week. And then we also went and started introducing this idea of this kind of a workflow, if you would, or this framework, which I'm just kind of tentatively calling ADJ, which stands for the steps in it, right? Analysis, design, justification. So the plan for today is basically to talk about those steps kind of in more detail and see, what do they look like? We're gonna talk to them basically at a high level, right? Just kind of, describe them, and then we'll actually go and basically start a problem. So kind of my second half of my slides is actually doing kind of what I would consider an AAJ problem. Now for you guys, right, the problems that I would ask you guys to do in this format are, I would say, relatively straightforward. So picking like a data structure, that's a relatively straightforward problem. There's not a whole lot of problems with ambiguity there, but that's because we're getting started, right? So as we go farther, right, you might get more complicated questions that are more, open-ended, right? They are more ambiguous, right? They are more ill-defined. You'll probably get that over time. But right now, kind of we'll start with things that are more simpler, right? So in a sense, what we'll be doing when we go through these examples, right, is a little bit of overkill, right? We're maybe spending more time and attention doing things than we really need to for the problem that we're working on. And the reason why we're doing that is for practice, right? We want to practice and make sure that we're good at this stuff on problems that are clear before we go to the things that are more complicated, okay? So yeah, so that's the plan for today, kind of what we're looking at. So yeah, let's go ahead and get started. So we have basically our three stages, right, of this ADJ thing, right? So the first one is analysis, right? So analysis, design, justification. So let's see, do I have a slide that has a, yeah. So this is my overview slide real quick, right? So just as a reminder, right? So we have these three different things, right? So analysis, design, justification, and they all kind of have different purposes, right? That are kind of important. So we're going to basically talk through these generically one at a time and then look at an example. Yeah, we might kind of, we will probably look at an example in slides because I have it already written out, but then we'll also probably talk through a different example as well, just because we can. So yeah, let's see. Okay, so analysis, right? So analysis basically is where we're looking at a problem and we want to figure out what's going on, right? Like what is my problem even about? So typically, right, it's actually where you spend the most time. So this sometimes I think seems maybe awkward to people, or either it seems awkward or it seems odd because like you're not used to doing it, but yet you solve a lot of problems. Some other idea, right, that you should always have some upfront time looking at your problem and trying to figure out what to do. Now, for some stuff, right, it's really straightforward, right? You didn't need to do, analysis techniques in your, calculus class because when they told you to take the derivative or to integrate this, it was like, well, I know exactly what I'm supposed to be doing, right? So no real analysis was needed there. Versus, right, you go to more complicated things, right? So maybe you go over to, 216, right? You're doing, UML for something. Well, then all of a sudden you need to spend a little bit of time doing your analysis to tell you what is even, what's even happening, right? When you have something that's more complicated. And so typically, right, if you look at stuff, right, if you look at problems and look at problem solving, the number one thing that you're going to spend time on is always going to be this analysis step, right? At least for the problems where it actually matters, right? I don't really need to, use any problem solving strategies when I'm doing something that's really small, right? Really, well, not small, but really simple, right? I don't need to think about anything too hard if I'm taking a derivative. It's only when you get to bigger things, right, that it's important. But somehow the idea is that whenever you're looking at your problem prompt, you can't really act on one that is, ambiguous, for example, right? We need to fix all those things, right? And that's what's going to cost us in terms of time, because we have to identify in the prompt, where are our issues? What don't I know? What do I know? And then for the things that I don't know, what can I do about it, right? How? Because I somehow need to fix those things, right? So if my prompt says something that's, I'm like, I don't know what that means. Well, what that should mean to you is that you can't really proceed. You can't do anything else because you're going to be basically building on unsound foundations, right? You might, think that it means something, right? Start working the problem. And then when you come back to it later, all of a sudden you have a different interpretation. Now all of a sudden things go wrong, right? So I know I've had that happen to me when I'm working on homework. I was like, I'll work on a part of a homework, right? And I'll think I know what something means. And then I'm like, okay, I'll finish this tomorrow. And then I come back the next day, and all of a sudden I don't know what I meant the previous day because it doesn't make any sense, right? And the issue there is that when I was solving that problem, something in kind of the statement of it, if you would, was unclear to me, right? And I couldn't really tell what was happening there, right? And all of a sudden, yesterday Ruben disagrees with today's Ruben, and now tomorrow Ruben will actually basically have to go and rewrite everything from scratch because they didn't do it right. So what you really want to do, right, is spend up time up front to make sure you really know what your problem is, right? And what that means basically is definitions, right? Saying this means this, this means this, this means this, right? Whatever kind of the problem gives you, right, you should bring those things up, right? And then whatever kind of leads from that, right? So sometimes, right, they say, okay, this is the way the world works, and then you can kind of see, oh, because the world works that way, that also implies this, right? So those are corollaries, right? What else do you get from your initial definitions? And your goal somehow, right, analysis is basically just to work on the problem itself. Don't think at all really about how you're going to solve it. I mean, you can if you want to. It's kind of hard not to, but in principle, right, you don't really care about how to solve it. All you care about is understanding the problem itself. That's what is of value, right? Because initially, right, if you're looking at a design problem, you don't really know what you're going to have to do in order to solve this problem. I mean, it could okay, so the stuff, right, we do is maybe simpler, right? But you can imagine, right, once you get more and more tools kind of in your mental tool set, you won't really know what to apply, right? And that's okay, because your first step here, right, is just to understand the problem, right? A lot of times what happens is in the analysis section, there should basically be stuff that you don't need, right? So for me, I always find it, kind of suspicious if I get a homework assignment, an ADJ assignment, where basically the analysis only has the stuff you need. Because the thing is that before you solve the problem, you don't really know like what's out there, what you could possibly do, right? Usually for a problem, there's different ways to solve it, right? So we talked about, right, that notion of design, right? There's going to be different possible solutions, and we can't really judge one as being better than the other, right? Because there's kind of some qualitative sense there. And so typically how it's represented in analysis is your analysis will have things that you don't need, right? Because maybe you thought this was relevant at the time, so you wrote it down, you defined it, and only once you got to design did you realize that it wasn't actually important, right? Maybe there's kind of a red herring in the question description, right? And you don't know what you thought it was important, but then it really didn't mean at all anything. And so again, right, this is typical, right? Because your goal, right, is just to understand the problem. You're not trying to solve the problem. You're just trying to understand how it works, right? And if you're trying to understand something, you kind of want to see it from all possible viewpoints, right? So you're definitely going to have stuff in there basically that isn't really needed later on. All right, so there are kind of 4 rough steps to doing this, right? So I have them kind of written out there. So maybe I'll just read the steps here. So 1, right, identify and address ambiguities, right? So look at your question prompt. What are you unsure of, right? What doesn't look good to you, right? What is stated in words that are unclear to you, right? Look for those things, right? And then once you know those things, right, you got to give them definitions, right? You have to say, okay, the user, asked for a brightly colored screen, and we're going to define that to basically mean the user wants to see, a color palette that has, at least, 10 different colors, right? Something like that. You want to basically, right, look at those ambiguities in your question and make them non-ambiguous, right, by picking definitions, right? And that, right, is a little bit of work because you always have to ask yourselves, is it reasonable or not? Sometimes what is reasonable varies from person to person. For you guys, I would basically expect that you, like, if I give you stuff that has, it requires all sorts of reasonable assumptions, like somehow a reasonable assumption is a defensible assumption, right? So if I say, why did you assume that? You instantly can tell me, oh, I did it because blah, 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 right? Versus it sounded okay at the time type deal, right? So yeah, so we want to do, so then, right, we have our definitions, right? For basically kind of the elements of the problem, right? So if we're talking about a user interface, right, maybe we were defining how colors should look, defining how buttons should look. I don't know. I don't know if I like this UI example. We'll stick with it for a second. All right. So your problem, right, has little pieces inside of it. You define those pieces, and then once all the pieces are defined, well, then restate the problem, right? You should basically, with your definitions, be able to restate the problem in a way that is more sound and more well defined, right? So it's basically like you're rewriting the question prompt. And the last thing here, which people I think usually miss out on or forget about, is that you need to define some metrics to tell you what a good problem looks like, right? So for us, right, working, so many academic problems, we may be used to seeing a rubric for everything. A rubric is basically a metric, right, or a measure for us to see, how well you did. Well, in the real world, you don't have a rubric to go off of because you don't know what the answer looks like. So instead, what you would want to do is define some metrics that basically say, oh, this is what my expected solution looks like. This is how I know that I'm done. This is how I know that I've done a good job, right? And that's something that people kind of skip, right? They're just like, okay, here's the analysis, here's the design, right? But they forget about, I have to have some way to tell you that this is a good answer. And that's what metrics do for us. Okay. So yeah, so let's move forward. Then I think maybe we'll have some. Let's see. I'm trying to remember what's the next place that I have question marks for you guys. Maybe it's on the next slide. Maybe it's not this one yet. All right. So just some more details here. Okay. So definitions. So this I don't know. Well, I don't know what rants you guys have heard. So if you take a kind of upper division math, you may hear people talk about this. This is one of the things actually my advisor always. Well, one of my advisors. I had two advisors when I was in graduate school. I had co-chairs. This is one thing that one of them always harped about. It's basically, so right initially that if you're looking at a problem, there's going to be some ambiguities in it, and pretty much every problem you look at will have ambiguities in it, and that's really just coming. For me, I would say it's coming from the fact that most of the times when we look at a problem, that problem is given to us in terms of like plain English, and human languages are a little bit weak, right? People don't always agree on what all those words mean, right? Words mean things, but the problem is they mean things to different people. So typically, there's some sort of ambiguities there. So what you really want to focus on when you're looking at a problem is trying to get some kind of concrete definitions for it. Like, what do you really mean, right? Somehow your definitions are, they're what counts, right? So sometimes, right, people always ask themselves, is this right? Can I do this, right? Is it okay? Well, your definitions are what answer you there, right? Your definitions, right? It's like you're defining what is true, right? What is real, right? What is actually correct, right? And it's up to you to define whatever you want, right? You can do that, but they're kind of your concrete foundations of against which everything else has to be built on, right? They're the kind of the gold standard that you measure everything by, that you judge everything by, right? Whenever you're kind of confused and you don't know, is that, okay, right? You always look to your definitions. Your definitions can guide you. They can say, okay, this works or this doesn't work, right? So they're very important. If your definitions for a problem aren't down correctly, basically you're going to end up at some point in time, right, where you're going to have a disagreement, right? You thought that it meant, I thought that this meant A at this point in time. Then later on I go back to it, and now I think it means B, right? And I have a disagreement, and all of a sudden everything breaks down. Not a good position to be in. And the way you address that, right, is by having definitions that you follow, right? That basically define how, you're interpreting this, okay? So some quick examples down here. So obviously, right, we need to find the ambiguities in our problem and then define them out. So a couple examples, maybe relating to the stuff we were talking about last time. For example, right, if a problem says display, right, we all want to be more specific, right? So, print each element in the collection exactly once in any order, right? Because when I say display, I'm not really making any requirements, right? If I say you can, display the array A, B, C, right? Like, you just imagine, right? You have a simple problem. It says, display this array, right? And the array contains A, B, and C. There's nothing in there to tell you, should you do A, B, C, C, B, A, B, A, C, or, maybe you don't even have to print all the elements, right? I don't really know, right? Display is actually a pretty open term. For us, we kind of naturally think of it as being, oh, I'm going to print every element top to bottom. But that's not, required, right? It could mean something else as well, right? So you can imagine if you're talking to someone who's, imagine you have a customer writing a specification for you, right? Even if display means something like that to you, right, it might mean something different to them, right? When they say display, they might mean that it needs to be, you need to open a new window on the screen and then put everything in there, right? Versus you're like, oh, maybe display, I could interpret it as just being print a bunch of text to the console window, right? So there can be kind of disagreement there. And disagreement is pretty kind of common when you're going kind of between, what would be the right term? I guess types of stakeholders, right? So the way you use the word, the way a vendor uses the word, the way the customer uses the word, the way the boss uses the word, all those may be different, right? And so you want to basically be sure what is it that we actually mean there. Another example there, efficiency, right? So let's say a problem says, solve this problem efficiently, right? What does that mean, right? In terms of what we saw in class, maybe we would interpret that as run in a big O time that's polynomial, right? Like what does it really mean there, right? Because people could have different definitions, right? So we may have some disagreement, right? The kind of the wording I have up on there is sort of the academic stuff, right? Like, it's got to run in polynomial time. If you're working on stuff in practice, when someone says efficient, they might actually be saying make it run as fast as it could possibly run, or make it run in constant time, or something like that, right? So when we see words like that, right, again, we don't know what the meaning. We got to write them down somehow, right? We got to indicate what they are. All right, so that's good for our definitions. Let's take a look at, let's take a look at some tools. So we're looking at a problem. We know there's going to be ambiguities. We know we need to fix them. What can we do? So here's kind of three main things here. Okay, so the first one, right, is make reasonable assumptions, right? Reasonable is in bold. Reasonable is the problem is it's both difficult to make reasonable assumptions, and also it's subjective to make them, right? So that keyword display on the previous slide. How do I what would be is it reasonable to basically assume they wanted to show everything one after another, right? Is that reasonable? Probably it is, right? Probably our intuitive definition is okay. The problem is So the problem with reasonable definitions sometimes is you look at that, you look at something, you use your intuition, like, oh, it probably means this. And then it's like, well, okay, we'll say that it means that. Well, we'll define it that way. But then every so often, basically, there's going to be something that's counterintuitive, right? You have kind of something being thrown in there, comes out of nowhere, right? And all of a sudden, it doesn't line up with your expectations, right? So we will also always want to be careful, right, that we're avoiding falling into any traps that are reasonable assumptions where, this reasonable thing is reasonable to me, but it's not reasonable to anybody else, right? I don't want to, be put in a position, right, where basically I make a mistake and I don't even see that I'm making it, right? So yeah. So the second one here, and actually I feel like maybe I should have even more emphasis on it than the other ones, is asking questions, right? So one thing that's kind of interesting sometimes to me is that people, if you give them a problem to solve, they seem to assume that it's self-contained and that it's like, that's it, right? Sometimes, right, questions aren't actually self-contained, right? Sometimes you do need to ask questions, right? Usually, right, questions are a way that you can basically deal with reasonable assumptions, right? So if you're doing a homework question, right? So let's say you're doing homework. That homework has some little bit of ambiguity in your prompt. You could either make a reasonable assumption, which puts you at a little bit of risk for making a bad assumption, or you could just ask, right? And it's important to think about those things explicitly, right? You have your choice there, right? So you don't always need to ask questions. Right? You don't always need to ask for clarification, right? You can always make a reasonable assumption. But the problem is your reasonable assumption, maybe it's wrong. Whereas if you ask a question, you say, okay, what did you really mean here, right? Customer, what did you mean? Well, whatever you get back is going to be true, right? It's going to be something you can rely upon. There's no sort of guesswork there that you had to do, right? You really did get back whatever information you needed, right? This is kind of underrated, right? People should do this more often. And I mean, technically, right, you can do everything without it, but it'll put you in a better position. It'll save you time, right? You can save time by just asking, right, for clarification, right? That should never be an issue. All right. So this next bit here, right, my third thing here is the idea of experimentation, which is I don't know, I don't know how many people use that word basically, and so I don't know if you've been told, experiment with something. Maybe you've heard the phrase, play with it. So, which is actually kind of a different idea. The idea of experimentation is basically, it's coming from science, right? The problem there, right, is that you're faced with the unknown, and you're trying to understand the unknown. And so what you do, right, is you maybe take a guess, you try something, and then you look at the result and find out what happened, right? When you do something like that, you're basically learning a little bit, right? So maybe what happened is what you expected to happen, and therefore you have some evidence for, the world works like you think it does. Versus you get something that's completely different than what you expected, well, then that's evidence that what you thought is completely incorrect, right? And so, the scientific method, right, doing experimentation, right, these are basically techniques we want to use when we're faced with the unknown, right? So I don't know what is happening, right? So I can't make a reasonable assumption, right, because I don't know. There's nobody to ask a question to. So what do I do? Well, make a guess, right? It's not going to be a reasonable assumption. So it's just a guess. And try it and see what happens, right? And you'll, in the process of trying it, you'll learn a little bit more about what your problem looks like. Repeat this a few times, you gather some more information, and then you'll put yourself in a position where you can make reasonable assumptions, okay? So this is something I think people kind of forget about, right? But sometimes, right, nobody knows, right? And when nobody knows the answer to something, right, play with it, experiment, see what you can figure out, learn what your problem looks like. All right, so my first question marks for you guys. Have we learned any kind of air quotes, experimental methods in this class? Is there anything we've talked about before with experimentation? You guys remember anything? Feel free to either jump in with voice chat or you can use text chat as well. My preference typically, right, is for the voice chat though, because the voice chat I can actually see, well, I can actually hear. I shouldn't say see. Actually, I can actually hear what's going on, rather than being like, oh, the text chat, got away from me. So, what do you guys think? Have we seen any experimental methods in this class?
Well, some of the homework you assign us sometimes feels pretty darn experimental.
Okay, good point. Let's see. Is this right side, Jacob? I think this is right side, Jacob. What do you got?
This is left side, Jacob.
Ah, I'm gonna have to label you guys in text chat. Left side, Jacob. What do you got?
There was that empirical process for to help us determine, I think, the growth of like the time complexity for certain algorithms.
Yeah. So that's the big one, right? Is that back when we talked about analysis of algorithms, we kind of introduced empirical stuff, and we said, okay, I have a black box. I don't know, how long it takes to run. And then we had this little loopy thing where it's like, okay, let's try an input size, see how big it is, right? And we did that a bunch of times to gather a bunch of data, and then from that, right, we created a model, right? And then we used the model basically to predict how long the algorithm would come. And eventually, right, we did the induction proof stuff too, which is kind of a separate thing. But yeah, that's the main thing we've talked about, right? That's the kind of our experimentation that we've done, okay? Is trying to figure out, given that I have a black box, I don't know what's inside of it. I have no idea what could be going on, right? I don't know. I don't have any kind of reasonable guesses that I can make, or reasonable assumptions I can make because it's a black box. Play with it and see what results you get back. So yeah, that's basically the one that we've talked about. Let's see. So the last one here, and I'm just wondering here, have you guys seen anything? Has anybody else talked to you about experimentation, or just air quotes playing with it? Has anybody else in any of your other classes in SER talked about stuff? I know they'll probably do stuff in your when you guys take your science requirements, but in SER, has anybody talked to you about experimentation? Any other, or anybody know any other experimentation that typically is common for working with software? Any ideas there? Have you heard the word experiment before? Have people talked to you about it before? Anything you guys have had before?
Findler had us experiment a couple times with GUIs and linked lists.
Okay. So one sense of experimentation, right, is exploration, right? Of saying, okay, I don't, know how to use something, so I'm going to try it, right? I'm going to try using the Java API, right, and see if I can build something, right? So that is actually technically an experiment, right? Because it's an experiment basically where you're trying to understand how something works. I know it might seem a little bit weird to say that, just going and trying an API is an experiment, but it really is, right? Because initially you don't really know how this thing works, right? And so if you go and try it, that kind of gives you an opportunity, right, to learn how it works. That's one example. Another example that may be kind of more familiar is actually in debugging. So when you debug and you're like, oh, I want to try this, changing this variable or commenting out this line or that line, that's all experimentation, right? You're playing with it to try to see what works. Typically what people do, right, is when they debug their programs, they might just comment out a line and see what happens. That's one way to do it. The better way to do it is to, before you comment out the line, get an idea of what you expect to happen, right? Before you run it and get the answer, get a sense of, oh, I think this is the way it works. This should happen, right? Try to do it that way, right? That'll actually save you a lot of time in debugging, right? If you have an expectation of what you're looking for when you're tinkering with your program, okay? And that'll actually save you a lot of time, right? If you have kind of a more, I would say, scientific view on how to play with things, rather than just guess and check, which gives you more information. But the thing is, like, if you can have an idea that your guesses are good ideas, and you can learn from your guesses, that'll help the process go much faster. All right, let's see. So going back to my slides, we talked about most stuff here. So yeah, take all the knowledge you gain, right? And we did basically take that information we picked up, right, and represent that in some sort of a definition, right? So now we do our experimentation, right? We find out that this thing acts like this, write it down, right? Make it real, make it concrete, make it permanent. Okay. So let's see, moving forward. So this slide is a little bit awkward. So this is a very important topic, but it's also awkward to talk through at this point in kind of what we've done and this point in the curriculum. So I kind of mentioned this before though, right? So we need somehow, right, the idea of having a metric, right? I need to have some way to tell what is a good answer, okay? So that I'm all putting under my heading of metrics and measurements, right? Basically what I need to do is have some idea about how I can look at a solution and tell that it's a good one, right? And there are kind of different ways to do that, right? And you always want to kind of do this in analysis, right? Is basically define a couple of metrics to tell you, oh, this design is good, right? What does a good design look like? Okay, because, okay, and one aspect there, and I'm glad I glanced at my slides there, one aspect there, right, is that when you go to solve a problem, right, you're gonna oftentimes have different possible solutions that you could, use. And the problem is, how do I pick which is the appropriate one, right? Or even, given that there's multiple ones, how do I defend my answer as being better than somebody else's? Well, part of that, right, is to have these metrics that we can justify. We can say, okay, I did this way, therefore I solved the problem in the question prompt, right? If I meet this metric. So they're very, very important. And you guys will see examples later on. We should even get there today. So yeah. So there's a few things we're looking at in terms of metrics, right? So a metric basically is like a way to measure something, right? So for example, weight, right? Weight could be a metric, right? So I can weigh everybody in the class, right? I don't know how to do that with you guys all over the world, but I could in principle do that, right? So weight could be a measure, right? And I could use a scale to take that measure. Or height or something else as well, right? So we want to have basically different ways, right, to talk about our programs and say, okay, this program, according to this metric, it looks like this. According to this metric, it looks this other way, right? Something like that. So our metrics have a couple of requirements on them, right? So one is that they're, relatively useful, right? Or useful relative to my problem, right? It's not, well, it's not useful, right? If I say, okay, write an algorithm to quickly, let's say I ask you to write an algorithm to quickly sort a list. It's not that useful if you have a metric that's on the amount of space used, because the question is about do it quickly, right? Do it in as little time as possible. It's not about space, right? So there should be an alignment between the metrics we choose and then the metrics that our problem statement incurs, right? Don't tell me that this sorting algorithm is a good algorithm because it's also secure. There's nothing about security. All we cared about was getting it to be in the sorted order, right? So there has to be an alignment between our metrics and our problem statement. The next thing, right, is our metrics have to be, reliable, right? So there's a sense of accuracy and precision, right? And that's something hopefully you guys have seen in your science classes, right? When you've done your lab work, when you've done, right? So all of them, right, whether they're biology, chemistry, physics, right? All of them should have a lab, and they should hopefully have talked to you guys about this stuff. I need my metrics basically to be reliable in the sense that I can trust the results and be able to compare the results of one design with another design, right? If I get kind of different readings, right, for different designs, well then, I can't really, perform a comparison, right? I have a bunch of noise there. Okay, real quick, maybe I'll have you guys draw on my screen real quick. So I have this little picture over here, which I grabbed from the depths of the internet. So this is actually kind of the typical way they show accuracy and precision, right? So they have kind of a target circle, right? You can see little dots in there. Can you guys tell me which one of these is like, which one is ideal? Meaning it's high in accuracy and high in precision. So just throw like a mark somewhere down there, right? So you can just put it in like one of these one of the squares there. Which one of these represents high accuracy and high precision? Just real quick, so you guys have a chance to write on my board and wake up a little bit. Which one of these is going to be? Okay. I like the use of hearts here because this is your ideal thing, right? If you can have that, life is good, right? So that top one, right, is high precision, high accuracy. So it's high precision, right, because they all cluster together, right? And then they're also on point, right? So the black dot in there basically is representing your actual real value, right? So your real value here, right? Maybe it's the height of the person, the weight of the person. For the algorithm, it's their ability to do stuff. Okay. Somebody's going overboard. So yeah, so that would be the ideal situation, right? So basically, all of our answers are kind of the same, right? They agree. What about the one that's low accuracy but high precision. Which one is that? Okay, so that's one on the right-hand side, right? So here, right, we missed the mark, but we're at least all in agreement. And this, right, you can actually use, right? Because if you think about it, even though you're kind of deviating from the real value, if you're deviating in a way that makes sense, well, you can still compare things, right? Relatively speaking, they're all correct. You can imagine if you know the distance from that actual one to the, to the measured result, right? You could subtract it out, right? You could normalize, right? You could shift it over, right? You could do that. So even though, right, it looks a little bit bad, you can still use this one, right? And then let's see, the one that's let's see, low precision and low accuracy. Which one is that one? It's the bottom one, right? So you can see, right, we just have the dots. Just they're all spread out. They're all random, right? They're not on target. This is the worst. This you can't do anything with, right? It's basically, right, when if you try to look at two designs, you try to compare them, I mean, it'll just never match up, right? It'll be worthless. Okay, and then the last one there, right, I think is what was this? This was yeah, high accuracy, low precision. You should put the check mark before I ask you guys what it is, right? I don't know what that arrow there is doing. Somebody's going overboard. I wonder, like, I'm wondering if this is like how many people is doing this right now. Like this could be like one person, one really energetic person that had like a double shot for the breakfast, or it could just be like half the class. I don't know, but yeah. Okay, so those are kind of four different kind of ways where we talk about measurements, right? For us, right, we want higher accuracy, high precision, right? And if we need to, we can lose the accuracy a little bit. All right, so that's one aspect. Another thing we want actually is what we call efficient metrics, which means it shouldn't take me all day to apply a metric, right? So if I say, you know, my metric is, well, so my metric maybe is, you know, can make the customer happy. That might not be like, that's a nice metric to have, but it's not a good one from the standpoint of it'll take me a month just to go talk to the customer and figure out what they like, right? So maybe not the best choice. All right, so question for you guys. Have we learned any metrics in this class? So I'll expand that to other classes in a second. But as far as SER222, have we learned anything that we could use as a metric in this class? Left side, Jacob, what do you got?
I guess the way to measure growth or time complexity. So like big O notation.
Mm-hmm. So big O is our main metric. And big O is nice because in theory, it's going to be high in accuracy and high in precision. It's basically well agreed upon, right? So we have these little hierarchies that tell us that if we have big O of n squared, it's going to be for sure slower than O of n, or it'll be faster than O of n cubed, right? We have all these hierarchies. So big O is actually going to be our big metric that we can use, right? It's one that's kind of very reliable. Now, for other things, right, you're gonna have to invent your own metrics, but for us, right, this is kind of a starting point, right? So whenever we talk about efficiency, typically you'll say efficiency measured as in terms of, you know, big O is what you'll say. So efficiency is a huge one. All right, do you guys know any other metrics to measure software from other classes? I'm not sure. I'm not sure what you guys have heard or not, but any other metrics that you can use to measure
Officially, whether it works or not.
Whether it worked or not. Okay, so this is actually what we call a correctness metric, right? So you can basically say, did my algorithm do what it's supposed to do or not, right? That's usually a binary thing. And if the answer is false, then, you know, you throw away that design. Okay. Oh yeah, I forgot about text chat, so let me jump over text chat. Okay, so Joseph mentioned runtime. So that's basically goes into the big O stuff, right? So runtime performance, okay? Okay, so Ethan has another one, lines of code, okay? So lines of code is another metric. So I'm gonna have to clear the screen real quick. Actually, so I can ask you guys. I'm glad someone said lines of code. Let me clear the screen real quick. Clear viewers drawings. Okay, there we go. Which one of these blocks would lines of code fall into? So if we want to use lines of code to measure a program, where do you guys think it would fall? So this is, you know, accuracy, precision, right? Where would it fall? Is it high in both, low in both? Where do you guys think it would fall? So LOC. Where does LOC go in this picture here? What do you guys think? Which of these quadrants? Okay, so I'm seeing, okay, so we got so we're definitely in the kind of the non-ideal quadrants down there. Yeah, yeah. So for me, I think I would, well, I mean, it should probably be high precision because there's not a lot of ambiguity about what it takes to like write a program. But the problem is lines of code can change, right? So I press enter a blank space, all of a sudden that number changes, right? So between algorithms, right, that number isn't going to be at all consistent or the same, right? So I could use it, right, as a metric. But the problem is it's just very inconsistent, right? So that I would be not inclined to trust, right? So let's see. I guess we'll bash an LOC. So we'll say the LOC, right, goes down here versus something like big O goes over here, right? So if you're trying to show that something works, you want to probably use big O. You probably don't want to use lines of code, right? There are good measures and there are bad measures. All right. Let's see. Instructions per second. Okay, so that's kind of another efficiency thing. Okay. Let's see. Anything else we got? So there are other metrics as well that are standard. So you guys mentioned some good ones. Another one you may hear, or you'll hear soon if you haven't heard already, cyclomatic complexity, which is kind of the measure of the amount of like loops and if statements in your program. For us, somehow, what we're going to care about is the idea of efficiency, which is the first thing we talked about, and then correctness, right? Those are the two things that mean the most to us. All right, so let me clear that, and we'll move forward. All right, next step, design. So I know we spent a lot of time on analysis. That's as intended. Our next two steps are going to be relatively short. So design. Design is basically what you guys have been doing in all of your classes up until now. You basically, asked to do a program, asked to do, an essay or whatever, right? And then you go do it, right? You're basically creating that answer, from, you're pulling it from the void. That's design, right? Now, stuff we talked about before is basically is kind of the lead up to producing a good design, right? Rather than just a design that seems okay, right? We don't want to seem okay. We want to be right. So this basically is where you can apply all of your techniques, right? So all your different classes, programming and what else you guys have taken? Probably the programming ones are the most interesting ones, right? Whatever it is that you have, right? Once you get out of this class, you'll have a lot more things that you'll learn. Take all of your technical techniques, right? Apply them right to everything you figured out about your problem when you did your problem analysis, and then you got your design. Now, designs can look a couple different ways. Up until now, right, we've kind of been talking about, problems where, let's see, I think I have it in a notepad somewhere. So we had problems like this before, right? I gotta close that thing and then go here. So we talked about problems like this before, where basically, right, you had this little problem statement here, and you said, okay, consider blah, 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 would use an array or linked list. The design here is actually like the keyword array or the keywords linked list. Sometimes people want to like write a program. That's not what this is asking for. This is asking for you to write a problem, to write any code. It's just asking you to make a choice, right? So the very simplest design you could actually propose, right, is basically just a choice, right? So I can buy A, B, or C. I need to pick one of them, right? I can just pick one of them from that list, right? So that's the way my problem looks, right? And I think it's kind of deceptively simple. Usually it's like people are like, oh, I need to do more work. But no, your design here can really just be, one word, right? Because you're just making a choice, right? Do I do this or do I do that, right? So yeah. Now in other questions, right, it's a lot more complicated. So for example, let's say I'm asking you to design an algorithm. If I ask you to design an algorithm, you're not going to be able to just give me a one-word answer, right? Your answer is going to be a couple hundred lines of code, right? So basically this is going to look different, right? So your answer might look like a choice, right? It could look like an algorithm. It could look like an argument or an explanation, right? So maybe something looks like an essay, right? It depends on what your problem prompt is, right? Some other note for you guys is that sometimes the design is really simple and sometimes it's really complicated. And it's where you get a chance basically to show off all of your kind of technical skills, if you would. All right. And yeah, that's actually my one slide for design, so we can move forward. So justification. This is kind of, well, for me, I would consider this to be the most important part. Usually anybody can do design, right? So usually anybody can sit down and crunch out some code. Anybody can point on the paper and say array or list, right? Design for me, I think, is not a big deal. Opinions on that may vary, but my opinion is that people can do design. Where people get stuck is justification. being able to argue that their design is superior to other designs, right? I mean, so at a high level, right? You think about designs maybe as being these things that compete with one another, right? So whether you come up with multiple options, whether somebody else has different options, right? There's going to be, different designs out there. They're going to be competing with one another for the kind of the gold star that says you are the right answer. You are the one that I'm going to propose to my boss. You're the one that I'm going to submit to my instructor, right? You have all these different competitors, right? And so somehow, right, you need to basically justify that a particular design of your creation, right, is that best design. And that's the purpose of justification. So over here, right, so we have a design, right, basically what we want to argue, right, is that design is sound, right? So it all the pieces kind of make sense and go together, right? They solve the problem, right? And it's somehow optimal, right? Because we want to basically be able to justify that our design, right, is the one to pick, right? Don't go and hire someone else to do this, whatever it is that I'm giving you is already the best, right? So this is our goal here, right? Is we want to basically show that our design, is sound, right? Is well-founded, right? And then is optimal, right? And by optimal, what we typically mean is look at your metrics, right? So your metrics, right, saying, okay, this thing should run in polynomial time. That's the way you say that your answer is the right answer, right? And for the question I showed you guys real quick with the data one, right, the metrics would be different. I haven't solved that one. I'm going to do that and actually give you guys another example. But you basically want to look at whatever metrics you define earlier, right? So things you decided were important. Look at those. And then from that, basically, evaluate those metrics and see how does your design fare, right? And so your justification, right, is basically going to be you presenting your evaluation of those metrics as a way to tell a third party, hey, this design is the best one, right? I want to argue that whatever it is that I'm producing is the best, right? So you have your metrics, right? You evaluate those. For something like the question where you want to pick the array of the list, oftentimes what happens is you have to basically evaluate that metric for each alternative, right? So you need to say, oh, with this one, it would have taken O of one time. With an array, it takes O of one time. With a list, it takes O of n time. Well, you look at your metrics, right? You're like, okay, my only choices were this or this. This one has clearly better performance, right, based on my big O metric as opposed to this other one. Therefore, this is the right one, right? So sometimes you basically have to look at, you have to basically look at your competitors and beat all of your competitors, right? For list versus an array, it's a very simple thing. You just have two choices. Maybe you have a dozen choices, right? Then you need to have an argument of, I chose A, so B, C, D, E, well, all the other ones, right? Those are all wrong, right? So your justification can get really long there, right? You basically need to have a way to say that whatever your design is better, right, than all of the other alternatives, right? Where maybe there's a fixed set of alternatives, maybe in worst case, there's an infinite number of alternatives, which is we'll talk about in a minute. All right. Okay, and so then once you've done that, right, once you basically looked at you evaluate your metrics, which I know there's not a lot of numbering here, so maybe it may sound as if it's simple, but it's generally not simple. Once you've done that, then you can say, okay, yeah, I am good to go, right? This is the appropriate answer. And so kind of everything comes together, right? You did your analysis. Because you did your analysis, your design made sense. And then because your design made sense and it was built on your analysis, then you were able to justify it, right? So then kind of all these pieces just come together. And what you're left with, right, is a solution that is right. And it's right, right? It's not a guess. It's not, I think it is correct, right? Assuming you've done all this stuff, it is right. Right. So for example, right, in theory, right, in principle, right, if I were to ask you guys to solve a problem using this framework, you would know it's correct before you submit it to me, right? You would know your grade before you gave it to me, in principle. Now, how that works in practice, that's kind of an ongoing experience for me as I teach this stuff. But in principle, right, you should know that you're correct before you show it to anybody else. Right? You should have the ability to verify it, because you're always trying to make sure, right, that one thing follows from another, that you're talking about what's important, right, that you're having ways, right, to support what you say, right, against something that somebody else could say. So yeah. All right. Questions, comments, concerns, complaints, critiques. Anything you guys got? Otherwise, we're going to start actually. I have a couple. I want to basically talk about this stuff applied to algorithms specifically, and then we'll start working on a kind of an extended example. So anything you guys got for me before we start looking at that stuff? All right, so let's go ahead and move forward. So ADJ, algorithmic ADJ. is the name of the section. All right. I feel like I probably talked through some of this stuff already. So before, right, our typical examples were things like we said, okay, pick array or a list. Pretty simple. Now we're talking about algorithms, right? How do I solve a problem that basically is asking me to write an algorithm? It actually ends up being kind of tricky, right? And it's tricky because of two things. First of all, design is more expensive because, hey, I have to write a program now, right? Rather than just picking, you know, this choice or that choice, I have to actually write some code. So maybe that's, you know, going to cost me a little bit of time. But then also, right, it's hard from the standpoint of how do I justify my answer against all the other answers that are out there? Because if it's an algorithm, right, I mean, there could be basically an infinite number of answers, right? So how do I, you know, how do I show that the particular one that I came up with, right, is the correct one, is the best answer, is the appropriate one, right? That's a little bit tricky, right? And so typically what happens is we'll have to make some changes in terms of how justification works and also how the metrics works. Because basically, right, we have more competitors. How do I make sure that I'm better than an infinite number of other competitors? That's a little bit tricky. All right, so as we go through this kind of example, right, these slides are going to be tagged. So at the top, you're going to see basically, you know, analysis, design, justification. These little tags basically to show you what each slide is talking about. As we go through this example, there will be slides where basically we like divert for a second from the example to introduce something a little bit new to you guys. As we work through this kind of problem, right? So I'm gonna apply the ADJ framework, which is we've spent time on it, so I think we all understand it. As we go through and try working this with a problem, what will happen is there'll be kind of, you know, other techniques they need to grab. So later on, there's going to be slides where, for example, I'll show you guys how to do a proof of correctness or a proof of termination. We'll do a few little techniques will become basically sprinkled in with whatever it is we're working on. So just be aware, right? There'll be kind of a little bit of a difference in flow of control as we jump through, as we go through this set of slides. All right. So I think we're good there. Let's jump forward. So our justification for working with algorithms is going to be a little bit different than what we had, you know, in the simpler problems, right? So in a simpler problem, when we're asked to, for example, choose array versus list, it's sufficient for me to do something like say, okay, list is O of n, array is O of 1. That's enough, right? And I can basically say this one's faster, it's the best choice, and then everything is done, right? But the only reason I can do that is because I have kind of a finite list of things to choose from, right? So if I'm doing a design, air quotes, right? My design boils down to a simple choice, and there's only 2 categories to choose from. So as long as I look at each of the categories and argue that this one's the best, then I'm good to go. The problem with algorithms, right, is you have, you know, this search space or solution space of all these different possible algorithms that could solve the same problem. So then how do you justify that the particular one you came up with is better than somebody else's? Well, the way you typically do it is by kind of thinking about your metrics a little bit differently. Instead of saying that you are, you know, the best answer for this metric, what you want to say is that you're as least as good as the best one, right? So it's kind of a different sense there, right? So saying I am the best was what we talked about before. Now you want to say we're at least as good as the best. Because when we say we're at least as good as the best, what that implies is there's no need to find an alternative design because we are effectively the best, right? There might be somebody else like me, but I am indistinguishable from them because I am at least the best, right? So it's a different way of thinking about it, right? And that's what we need to do, basically deal with the fact that there are so many different algorithms out there that could be possibly be written, right? If we want to show that we are the best, well, then that means we're going to have to list off all the possible algorithms that could solve our problem. But that's basically something that's impossible to do because there are an infinite number there. So instead, what you want to do is you want to show that, you know, we have, you know, we're at least as best as them, right? So that's our thinking we're going to use here. Now, when we pick our metrics, right, some of our metrics are going to be for functionality, right, or correctness. Some of them are going to be for performance, right? For functionality, we're basically going to say that, you know, the solution should have feature X, right? So if any algorithm supports that feature X, it's at least as good as the best answer, right? So it's do I have it or do I not have it? That one's not too bad. For performance, things are a little bit trickier. Usually, if you have you say, okay, my metric is big O performance on the number of comparisons. What happens is you're basically obligated to do like a lower balance proof to say, okay, my algorithm, there is no faster algorithm out there, right? That's kind of what we're obligated to do, which can be kind of time intensive. Sometimes, you know, your questions may have something to help you out, right? They may say, oh, you know, it just as long as it's polynomial. But if your algorithm says something, but if your question prompt says something like just make it as efficient as possible, well, that puts you in a pretty bad position because you have no choice but to, you know, have to figure out what is the fastest way to solve this thing, right? And so we'll do actually a kind of a mini lower bounds proof here for this problem that we're going to be talking through. So yeah. All right, so slightly different flavor right over the simpler problems. Just some machinery to deal with the fact that when we're looking at algorithms, justifying an algorithm means justifying it against a whole host of other alternatives that we can't really see. All right, I guess I'll move forward. All right, so the problem we're going to do is basically updating a priority queue. So priority queue is the content we did kind of not last week, but a little bit before last week. The idea there, right, is we had this data structure that we kind of could have, partially stored, where we could, throw stuff in the array, right, and we could easily, get out the largest thing, or add in an element that is, that is new, right, and it would kind of update this thing, and it was nice because it let us add elements in log time, and also let us, remove elements in log time. So yeah, so this is modulate. Now, when we did it in class, right, we basically just did the two operations. So we did delete and we did insert, right? Those are the two we did. And we kind of actually assumed that the contents of our priority queue were immutable, meaning they don't change inside, which is actually important, right? Because if you change the priority queue of something, if you change the priority of something, all of a sudden it might not be in the right position, right? So you can imagine that you change the priority of something to be really high. Well, if it's buried in your priority queue, you're not going to, update that priority queue. That large number will be stuck somewhere in the bottom, right? And all of a sudden it'll be out of order and all the algorithms will break. So a potential new method we can actually implement for a priority queue, which is what we'll do in this example here, is an update method for I need to update the priority of this node to be this new priority. So go find that node, update it, and then adjust the tree to be in the proper order. So that's what we're going to be looking at doing. That's what we're going to do our AUJ stuff on. All right. So that's our plan here. Let's start off with analysis, right? We always got to do things in the right order, right? So start with analysis. So things that we need to do, right, is basically we need to, better define the problem, right? So what is meant by updating a priority queue, right? Do I need to make any assumptions, right? What are the metrics, right? So this is kind of all standard stuff, right? So these kind of bullet points are coming from what we talked about earlier, right? Define the problem, define the metrics, right? Understand your problem, right, is what we're looking for, right? Then once we're done with that, we need to create some pseudocode for the algorithm, and then we need to justify, right, that whatever it is, our metrics that we pick, those are indeed things that, our algorithm satisfies, that it meets, right? We need to have all of these things. All right, so this is our rough layout, so we'll go through these kind of one at a time. So let's start with a problem statement. So I have it kind of written up here for you guys. And I would maybe either screenshot this or either download the slides from Canvas and have it open. We will maybe have to come back and talk about the problem description a little bit. So yeah, so this is a sample problem, right? So this is a little bit more complicated than stuff we've seen before. Not quite a real world problem, but getting there, right? So things will get more complicated over time. So yeah, let me go ahead and read this out and we'll see what we got. Define an efficient algorithm to update the priority of an entry inside of a priority queue. Analyze the problem, design an algorithm for updating the priority queue, and justify the algorithm's optimality. Okay, so we kind of have two little parts of the prompt there, right? I have my basic problem on the left-hand side over there, and then on the right-hand side is, my little bit of a backing, just so I know what it is I need to produce, right? As you can imagine, right, this could be something I could see assigned right as a homework assignment. Okay, actually, let me double back. I see I missed the question from Joseph a little while. Joseph way back was actually asking about justification. You know what? I think that's actually a good question. Sorry I missed it earlier, Joseph. I think maybe I'll save that and we'll come back to that when we do the justification for this problem. Because so we're not always obligated to create different designs, but it is a way that lets us argue our justification. Easy way to do it. Well, actually, we'll plan to come back to that thought. I think that's a good thought. So yeah. Anyways, getting back to this slide. So this stuff over here, right? This is our problem, and this is just, I don't know, class stuff. I don't know. So let's look at this here. I think I kind of already answered the first bullet point there, right? I went through the slides, talked about, AUJ is a little bit different, right? For an algorithm, because you have to basically produce an algorithm, right, as well as be able to argue it against every other design that could possibly be implemented, right? That's a little bit tricky here. Let's jump down to these four and let me see if I can get some input from you guys. All right, so first question here. What do you guys think? Is it possible to solve this problem? My mouse got stuck there. Yes and no. We'll start with a poll and then I'll see if somebody can speak up. What do you guys think? Is it possible to solve this problem? Can I design an efficient algorithm to update the priority of an entry instead of a priority queue? What do you think? Yes or no? That's an N there, trust me. There you go. Can I do it? So one vote for yes. Yes, 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 yes. Okay. So yeah, this one doesn't seem bad. Pretty sure we can do it. I mean, worst case, we rebuild the thing from scratch using our sink and swim, right? So that shouldn't be any problem to do it. This one isn't malformed. I like how so I put the ellipsis in there, right? But like, yeah, this is not actually anything, right? There's not anything wrong with this, right? This is perfectly fine to solve this problem, right? It's not an impossible problem. Although, you know, someday, maybe I'll give you guys one. All right. Let's look at number 2. Okay, so for number 2, I'll read the question, and I'll add a little bit. Can this problem or a portion of it be solved by something we already know? So here, maybe focus on the or a portion of it be solved. So do we know anything that could help us out with solving this? Maybe not do the whole thing, but at least do part of it. A couple votes for yes. Okay. Anybody want to speak up with what they think could help us out with solving this problem? Either speak up in voice chat, put in text chat, or write on the screen. Anybody want to explain why they're saying yes there? What do we have that could help us? So we're thinking back right basically to module 8, right? What do we have? Okay, so Joseph's got sink and swim, right? So we already have basically methods that help us move up and down in a priority queue, right? Basically adjust things. Those can probably help us, right? So when I make a mental note, right? I have some functionality that could be useful. This, though, seems to be more generic, right? Because if I have to update a priority, right, it could go either up or down, and it could be anywhere in the tree, right? So sink and swim are going to be useful for exploration. So they'll solve part of our problem. All right. So another yes or no question. Are any parts of this problem underdefined, right? So it's like ambiguous, right? I didn't tell you enough. So just looking at this first part here, right? Is anything over here underdefined? All right, so if people say yes, what is underdefined? You can either speak up, write in text chat, or just circle the words. If there's words you don't like on here, circle them in that question prompt. If there's things you're like, I don't know what they mean there.
I would say how efficient.
Okay. I'll circle up. Okay. So efficient, that's one thing. How efficient? I'm not told here. Anything else? There's one big one here. Updating how. Okay, so updating it. So we don't know how to update, but probably that's something we can define. We can basically make on our own, right? Because once we understand the problem, we'll be able to create our own algorithm to do it, right? So it's not going to be something we look up from a book or the website, right? We're going to have to create it ourselves. All right. Is this the only thing that bothers people? Anything else? There's one thing that bothers me here. Okay, what visibility we have in the okay. So Joseph's onto something. It's actually something more generic inside of a priority queue. So I'll ask you guys. I'll start by asking you guys. I guess the biggest question here, which is something that nobody's talked about, is this a max PQ or a big PQ, or a small or min PQ? Probably most people here thought it was max, but does it say if it's a max or a min PQ? It doesn't. So we don't actually know what type of priority queue it is. That's the biggest thing here, right? So actually what we need is basically, we need to know max min. And the other thing we need to know, this is what Joseph was talking about, is we need to know the implementation, right? Because the implementation, what implementation are we adding this to, right? So if I ask you to add this to Sedwix, it's going to be different than if I ask you to add it to CLRS's implementation, because they do it differently, right? So both those things are unknowns. I don't know if it's a max or min, and I don't know the implementation, okay? Now, probably there's people here that are like, I would have never thought of that. That's why we're doing this as an exercise. That's why we're going through this. Because this is the stuff that they'll bite you later on. People always make reasonable assumptions, right? The problem is that when reasonable assumptions happen in your head without any checking, that's when we get in trouble. All right. So our first step, I guess I'll just talk about it. Our first step, right, basically is going to be to identify these ambiguities, right, and try to fix them with definitions, right? That'll be our first step. All right. I'm actually okay. So everybody got all these right. That's very encouraging here. Except for the person who puts the stars on the bottom of the screen. Like, I don't know what that's supposed to be doing. But, to each his own. All right, let's move forward. So let's try fixing it, right? So we got to fix this problem. We got to make this thing solvable. Otherwise, we're wasting our time. All right. So, okay, so our question prompt is here. And I just had, so there's kind of some main things here, right? So we talked about, right, max or min, right? What implementation? And I really should have had another one here. Efficiency should be on this list here. Efficient, how? All right. Has the letter A there. Just out of curiosity, what does A stand for here? One vote for answer?
I'm guessing answer.
Yeah. So it is the answer, but it also doubles up here. It's also an assumption. Right? So this sort of is where we get to pick how the world looks, right? So these are hopefully, right, these are the answers that we take as to be reasonable assumptions, right? Because the problem is there's nothing really in my prompt that could tell me either way, is this max or min Q, right? It's essentially blind to that, right? If we really want to know, we'd have to probably go and ask a question. I mean, we can't even do experiments here. We'd have to ask, right? What did you really mean, right? It's missing here. For the second one, like, so this, okay, so I'll just draw here. This I think is a I mean, it's an okay assumption. It's an okay assumption. Versus, I think this one down here, I'd say this is a good assumption. I don't know why I started in the middle of that word. This is a good assumption. Top one I have no evidence for. The bottom one actually I would argue, because I'll be like, oh, if this is a sign in SER222, they're using a Sedgwick book. They probably need to update the Sedgwick algorithm, right? So I did that. So yeah, that was kind of just I realized that this morning when I was looking at my sets, like, oh yeah, that actually stands. It means two things. It means answer and it means assume, right? It's our assumed answers to these questions. Like I said, top one I think is an okay assumption. It's the best we can do without knowing more, without asking somebody for more input. The bottom one I think is a decent assumption, just because you can imagine being assigned this in our class, what would happen. All right, let's move forward. So when you're asked to do something, right, it's always a good idea to try doing some examples on paper, right? So a lot of times, right, people want to just start coding. That's, I think, what everybody, always does at the beginning, right? When you have problems that you can do that. But eventually you get to the point where things are too complicated and you don't really know, what it is you're supposed to do, right? So doing examples by hand is a big thing. All right. So I'll just look at this really quick. So here, right, is a, priority queue, right? This is not actually a max priority queue right now though, right? There's something wrong with it. That 14 is sort of, out of order with respect to everything else, right? That doesn't look good. So our job, right, is basically take this thing and, somehow convert it to be this thing on the right. Right? And we need to get an algorithm to do that for us. If we're working on paper, what would we do? Anybody want to maybe draw on the slides? So if we were working on paper, how would I fix this? So you can imagine, right, we did traces in class, right, of having to basically update things. Yeah. So we want to basically, right, swap two things, right? So swap the 14 and swap the 10, and then we're good, right? That'll give us a result, right? This is the very simplest thing because I didn't want to have to draw too much, but you can imagine, right? It would be a good idea basically to go and, do a few of these, right? So imagine, right, something's out of order, you're being asked to update it. How do you do it, right? Well, this one ends up being, you've got to basically, swap something, right, and move into the position that it does belong, right? And this is probably, so this I would recommend from the standpoint of make sure you know what you're doing, right? Sometimes people start to work on things and they're not really sure what they're working on, and they'll end up wasting their own time because they basically didn't understand the problem well, right? You want to have some intuition for how things go together. That way, when you try to put the pieces together, they go together and they make sense. So yeah. All right, and so this is still our goal here, right? How do we get that? Let's see here. So we already talked about there's some ambiguities here, right? So I think we already highlighted, right? We're not sure about efficiency. We're not sure about the priority queue. So efficiency, I think we'll handle that in metrics, right? So we want to basically we need to decide what does our metric look like, right? Like, are we looking for a certain amount of efficiency? Do we want it to be as efficient as possible, or whatever it may be, right? So we'll handle that in metrics. The priority queue, we're like, oh, is it a max or a min? We'll handle that under definitions. Definitions. All right. And I think our main ambiguity, is over here in that part, right? With what it means to be efficient or not. Okay. Why did that not? I'm trying to clear stuff. Clear all drawings. Sorry, there you go. Okay. So we have ambiguity, right? Like the efficient thing, right? Like what priority queue it is. Then we wanted to create definitions, right? That's how we solve it. So I'm gonna go to the next slide. Don't freak out, please. So the right-hand side is all the definitions. So this is me throwing a bunch of math at a problem. Now, you don't always throw math at a problem. Math is overkill for a lot of things, but here we'll use it because, at least for me, I want to be right? And rather than using a bunch of words, right, I try to be a little bit more formal, right? Human words always have kind of that potential for ambiguity in them. Math, not so much. All right, so I have my initial prompt up there, right? And so we're going to assume, right, that it's going to be, a maximum PQ. We're going to say that it's Sedgwick's. And actually, we're going to add this little bit here, which I forgot to talk about before. We're going to assume that whatever algorithm we're using takes in a valid priority queue and produces a valid priority queue, right? Because that's not like, it's sort of hidden there in the prompt, right? You're going to update one that's existing. When you're updating one that is existing, right, it's implied that you start with one that's good and one that's also good, right? And so I'm bringing that assumption out so that I know, like, basically what I want to know is what requirements is my algorithm going to be subject to, right? So I'm making that specifically clear here. Hopefully these are all reasonable. I think they are. I won't talk to the right-hand side. If you guys go on Canvas, there will be basically a PDF that has these. These are me distilling down all the assumptions and definitions that I need in order to talk about PQs, right? So you can see I have to talk about binary trees, complete binary trees, maximum heaps, heap ordered arrays, and then priority queues, right? It kind of breaks down. And I need all of these, right? So I know exactly what I'm working on. Again, I won't talk about them right now. I'll let you guys take a look at them kind of offline because the PDF is posted on Canvas. All right, I have 1 minute, so I'll do one more slide and then we'll call it a day. So last thing, so we have our definitions, right? The final thing we'll define is what our algorithm looks like, right? So we know we're going to be writing pseudocode for an algorithm. So we know we're going to basically be writing a function. What does that function look like? This is my example at the bottom. Basically, what we're saying is, I know I need to write something called update that takes in, a node to change, right? Its new priority, right? And the result, right, will be updating the contents of the priority queue, right? And you can see over here, this is our priority queue model, right? So if I'm updating a priority queue, I need to have some way to represent it. Representations are called models. So you can see there, right, I have to have the n variable, right? Keys array, values array, right? That type of thing. So yeah. So this basically just helps me say, what does an answer look like, right? So an answer would be the stuff that I fill in over here, right? I can't really have anything else, right? This is what I'm trying to do, right? So yeah. So I've defined basically the bits of my problem on the previous slide, right? Now I've defined, what does an answer look like? The next step that we'll get to next time is talking about the metrics. All right, so that's all I got for today. So thanks for coming. And yeah, that's all I got. I guess have fun, and I will see you guys on Thursday. Current plan is to maybe do a partial class period on Thursday, maybe just an hour. So yeah, I'll see you guys later.